Welcome everybody, round 2. Still talking about uniform circular motion, objects moving in circles. We've already looked at the velocity and the acceleration, a very important idea. Now we're going to take that acceleration and see what that means for forces that are acting on it. And frankly, maybe spoiler, Newton's second law, that big topic we spent a lot of time before discussing, it comes right back here, setting up sums of forces, free body diagrams, okay? We're doing the same idea now just for things moving in a circle. All right, now let's make sure we understand what's going on. If you remember the diagram from my last video, we had this toy plane. It was attached to a string, and this kid is just whirling it around, just going around in a circle. Even if the speed is constant, it's accelerating, right? Because the velocity vector is changing, therefore it must have an acceleration. Is there a force acting on this little toy as it's moving in a circle? Absolutely. And I hope you recognize that there has to be some force, and I don't just mean gravity. There has to be some force that's causing this object to accelerate, right? Newton's second law says, hey, you want something to accelerate, you need to apply a force. And in fact, you need to apply a net force, all right? Another way to think about it, if you remember when we studied inertia, an object in motion stays in motion. Technically, the definition was an object in motion stays in straight line motion. When you take a bowling ball and you roll it down the lane, it wants to go in a straight line. This plane, whether you chucked it or threw it, it wants to go in a straight line. Gravity will cause things to arc up and down, and this string must be applying a force to cause it to change direction. And the plane's direction is constantly changing, it's constantly accelerating, therefore there must be a force that's acting on it. That's what we call the centripetal force, this overall net force that's following Newton's second law that causes an object to move in a circle. And another spoiler, it's called centripetal force. What direction is that force? Remember, whenever we were talking about Newton's second law, the net force always acted in the same direction as the acceleration. That's a rule, right? Here's Newton's second law, vector here, vector here. The net force has to be in that same direction. We learned in the last video that the direction of acceleration was towards the center. So the direction of the net force, this isn't super obvious, it's not super intuitive, but the net force on any object moving in a circle must, capital M, be pointing towards the center. Okay, anyway, let's look at Newton's second law. So now hopefully you maybe accept that there needs to be a net force. We can apply Newton's second law. Here's what it said. The sum of the forces acting on an object is equal to the mass of that object times its acceleration. We now know that for an object moving in a circle, the acceleration is this thing known as centripetal acceleration, A with a little c. And we learned an equation for centripetal acceleration. So all I did was I took Newton's second law. Instead of ma, it's mac. And oh, right here, this is now the mass. That's the same mass right there. That's not new. And then v squared divided by r. This is known as the net force for things moving in a circle, or the centripetal force. This right here is what we call centripetal force. That's actually important for a reason I'm going to get into in just a second. Centripetal force. It's this expression. It's really you applying Newton's second law for an object moving in a circle. Okay? Hopefully you have that written down. Next slide, just building off of this, all right? Some important ideas about using Newton's second law for objects moving in circles, all right? This is the net force required to keep something moving in a circle, as I discussed, all right? The centripetal force, it is not a new force. When we are talking about centripetal force, I know I'm switching colors, but oh well. The centripetal force does not refer to an individual force like tension or weight or normal force. When I say the centripetal force of the object, I am talking about the net force that is acting on it that's overall causing it to move in a circular path. Centripetal force is not a new individual force, it is the net force. Students are going to get tripped up. Okay, when I have us drawing free body diagrams, if you draw a dot and an arrow, okay, here's a force. What force is that? That's the centripetal force. Oh, no, no, no. The centripetal force is you applying Newton's second law, okay? And because, as we discussed with the direction of the acceleration, centripetal force is always pointing towards the center of that circle, okay? You know, it's one thing to see it as bullet points. Let's go over some ideas with an actual text and an actual diagram. All right, so here I have is kind of a clip art from maybe the 70s, it looks like, but I have this person, they're spinning almost like that airplane again. Imagine maybe they have a ball at the end of a string, and they're spinning that string in a circle, okay? Let's call this location right here location A, because they kind of have this front view and then this top-down view, and here's that location A again. All right, this ball, let's assume it's moving in a perfectly horizontal circle. Centripetal force is that force that's keeping it moving in a circular path. Now, this first idea right here, I'm sure many of you have heard of centrifugal force or centrifugal force. That is not what we are talking about. In fact, in this class, almost with the exception of just right now, we are never going to use centrifugal force. Now, it's kind of funny. If you go online or if you have some other past physics teacher or science teacher, they might say a centrifugal force is a fake force. It doesn't really exist. That's not true. Centrifugal force is a very real force. It's just not in the reference frame that we're going to worry about. This entire class, we've almost always had this reference frame where we're kind of standing back and we're watching something happen. Like right now, look at this picture. We're not an ant on this ball. We are off to the side watching this. We are seeing this ball moving in a circle that has an acceleration and a total force towards the center. That's centripetal. Centrifugal forces, that's if you have the reference frame of being inside of the ball. Or another example, imagine you're inside of a car when it makes a sharp turn. Well, you're in the car, you kind of feel this force pushing on you like you're flying out away from the car's motion. That is a little closer to centrifugal, but it's not a term we're going to use, and it's not a term you should be using on my own exams or quizzes, and frankly, not on the AP Physics 1 exam. So I want you to kind of get centrifugal force out of your mind. It's very real, but it's in a different reference frame, okay? Now, what is causing a force that sometimes might not seem like it's towards the center? Like we said that this ball feels a net force towards the center. But if you right now you found a string and you attached a ball and you spun it around in your hand, you would say, well, Mr. Thrasher, wait a minute. It seems like this ball is pulling my hand not towards the center, but away. And that's true for a different reason. It's almost a Newton's third law. The ball is being pulled towards the center. Your hand is being pulled away. But I'm not analyzing the forces on your hand. I'm analyzing the forces on the ball itself. Okay, the ball must be accelerating and must have a net force towards the center. Or another way to think about it, you're fighting the inertia of that ball. Remember, the ball wants to go in a straight line. Objects in motion go in straight line motion. The string is fighting that. So you're trying to pull, you're trying to tug that ball inward, keep trying to change its direction. So again, if you're not really clear about how you're analyzing a situation, you might be thinking, well, it feels like it's going outward, not inward. That has to do with what you're feeling versus what the ball is doing. It gets a little complicated, I admit. Okay, but still, for the object moving in a circle, the acceleration is towards the center, and therefore the net force must also be towards the center. All right? Now, that's enough just me going over ideas. They're a little vague. Let's actually look up a sample problem. Let's work through a sample problem. It says right here, set up an expression. We're not going to actually calculate any numbers, but let's set up an expression for the speed of this ball using Newton's second law. What I have right here is I have that same picture. This girl is swinging this ball in a horizontal circle. Let's assume it's nice and perfectly horizontal, and let's set this up for the object when it's right here. Let's call this location A, all right? So what's the first thing we normally do if we're using Newton's second law? Well, I like to draw a free body diagram. Okay, let's draw a free body diagram for this object. The object is right here. I bet you can tell me one force that is absolutely acting on this ball at location A. If you're saying mass, absolutely. So right here. You could write mg, you could write w, you could write fw. Remember, doing forces, you could often write things in slightly different ways, and the college board, the teacher, the professor, they'll know what you're talking about. So that should be acting straight down. There's the weight. What's another force? There's a force acting towards the center. I'm going to draw an arrow that's horizontal. What are you going to label that? If you are going to write down FC, that is incorrect. The centripetal force is not an individual force. It's the net force. There is very true a force acting on it towards the left, but that's simply the tension. That's the string that's acting on the ball, right? Forces have to be coming from things. We know that gravity is pulling the ball down, and it's this string that's pulling this ball to the left. Something else. Maybe you're thinking, well, wait a minute. When the ball gets over here, isn't the string now going to be like this and pointing this way? You're absolutely right. So to be honest, it's usually helpful, at least in your brain. You don't necessarily have to write it down. I like to, but make sure we're clear where we're drawing this free body diagram. Because for things moving in a circle, technically at different locations, the forces might actually be pointing in different directions. So this is the free body diagram right here at A versus maybe at B or C or D or some other location, okay? But this is a free body diagram for this object. What's our next step? Usually it was incorporating or recognizing what is our positive and negative direction. The same step is important. Let's say that positive is upwards. That's how we normally do things. But what's going to be the positive direction, left or right? Now, we used to say left or right and left it at that. But again, as this object is moving in a circle, sometimes this tension is pointing left, negative maybe. Sometimes that tension is pointing right, positive. That would be confusing. There's actually a bit of a new way to think about direction for objects moving in a circle. Let's think of it in terms of towards the center. Remember, in that centripetal direction, center seeking, towards the center, let's call all forces towards the center as positive, and forces that are away from the center as negative. You don't necessarily have to write this all the time, and later on, we will see examples of forces that are both towards and away. In this example, there's just the one force. But now since we're dealing with accelerations and forces towards and away from the center, it makes sense that that's our coordinate system. Forces towards the center are positive, whether it's, to the left over here or to the right over here. Both of those, if I say towards are positive, the tension will be positive, and away is negative. You'll get a lot of practice in your class with example problems. I know this is a little weird, a little iffy at first. Like usual, you'll get practice. But that's how I'm going to set my positive and negative directions, okay? All right, well, next, let's try and write out the sum of the forces. I could set up the sum of the forces vertically, but let's just do it in this horizontal, in this centripetal direction. The sum of the forces in the centripetal. Well, what forces are acting towards or away from the center of the circle? Is it the weight? Nope. Just like before, if those vectors are perpendicular, they don't affect one another. There's only one force that is acting either towards or away from the center. That's the tension. Now, am I going to have tension be positive or negative? I'm going to have it be positive because this tension force is always pointing towards the center of the circle. Again, whether it's here or here, that's the benefit of what I have written in blue. Okay, it's always towards the center. That is equal to ma. Now, that's the centripetal acceleration. That's mv squared divided by r, where r, it would probably be given in the problem, or it's what you're calculating. That would be the radius of the circle, maybe something like that. Maybe that's my r, okay? Now, again, there's no numbers, but if I was to solve this for v, all right? Well, I have right here, I'm going to move myself right there. So I have t equals mv squared divided by r. So that means that t times r divided by m is equal to v squared. Take the square root of both sides, blah, 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 blah. So that v would be equal to the square root of t r over m, okay? Now, more or less, this is the same second law stuff we've been doing before. Yeah, some weird and unintuitive at first differences with how we're calling positives in negative direction. And again, the centripetal force is just you applying Newton's second law. It is never showing up in a free body diagram. Just think what forces are acting towards and away from the center of the circle. Okay, maybe there are vertical forces. Set up Newton's second law just like we've normally done. And then you'd be able to solve for things, okay? Of course, you'll get a lot of practice in class or in any workbook you have. But that's all for this video. Thanks a lot for watching. I'm signing out. See ya.